Hybrid orbitals is a difficult concept for students to understand, and it's somewhat difficult to visualize as well. I'm going to use some balloons today to help, hopefully, the students to be able to understand something about what a hybrid orbital is. Let's start at the board first to look at the electron configurations of what we're working with. Carbon is the king of hybridization. Carbon with its 4 valence electrons would normally be expected to have 2 electrons in the s orbital and 2 unpaired electrons in the p orbital. Hybridization is a method that scientists use to explain the mysteries and the wonders of bonding. If I were to ask you to explain what love is, you could all give a definition, but it would be difficult for us to arrive at a single definition of what's happening. Well, hybridization is a way that scientists try to explain the mysterious process that takes place inside of atoms using concrete things that we can look at. So as any model, it's incomplete, but it helps us to get a picture in our mind. If carbon had 2 s electrons and 2 unpaired p electrons, we would expect to see some subtle differences in the bonding that would take place, for example, in a molecule of CH4 methane, where we have 2 of those would be sharing an s electron and 2 of the electrons would be a p electron. That's not what evidence shows us. So scientists have developed a model called hybridization in which they say that the carbon, for reasons of energetics that we'll not go into today, but that carbon takes one of the paired s electrons and it promotes that into a p orbital, so that instead of having the typical s2p2 configuration, we would then find an s1p3 configuration. Then what happens is that those s electrons and those p electrons, they combine together in different combinations that we'll represent with balloons here in a moment. If carbon takes its s electron and all 3 of the available p electrons and puts them together into the atomic mix master blender, puts them on puree for a few moments, it comes up with 4 completely similar, very homogeneous orbitals that we call sp3s because it's made from an s and all 3 p orbitals. If, on the other hand, the carbon atom takes and puts the s electron and only 2 of the p electrons that are available into the atomic mix master blender, then what it does is it produces an sp2 orbital, and 1 of the p orbitals remains unhybridized, and we'll look at that in a moment. The last example is that if we take the s electron and only 1 of the p electrons, leaving 2 of them unhybridized, then what we have is called an sp hybrid, and that will produce a slightly different configuration. Now, if we come back and take a look at that with balloons, I think that we can see a little bit of common sense with the process. If we take the 4 balloons, and the technique that I use to tie the balloons is a technique that we use for different types of classes. I'm going to take the 2 balloons, and I'm going to take and stretch one neck out, and then I'm going to twist it around the neck of the first balloon. And I'm going to wrap it around there maybe 2 or 3 times as I've got that neck stretched out. Then I'll reverse and I'll stretch the other balloon out and wrap the neck of the second balloon around the neck of the first balloon. And I know that's difficult to see, but the technique is such that you stretch them out, and then when you release those balloons and the necks, the compression pulling that back in keeps those balloons temporarily locked together so that we can use them for our demonstration. So what we have is this is an sp3 hybrid. This is 1 electron, not a pair, but 1 electron of what we would call the sp3 hybrid atom. So we're going to see, as from the board there, that there are 4 of those when we have our sp3 hybrids. So here are 3 of the sp3 hybrids. And here's the 4th one. Since these are identical electrons, here's the carbon atom in the center. This is an sp3 electron, an sp3, an sp3, and an sp3 here. These 4 electrons are negatively charged and they repel, and the shape that they result in is a completely uniform tetrahedron. The bond angles here would be exactly 109.5 degrees, and this is what we believe the methane molecule would look like. For example, CH4. There would be extreme uniformity and regularity in the molecule, and that process takes place and we have the sp3 hybrid. Now, if I could have just a moment to make another set of those. We twist the necks of the balloons together. And we add a third. And we add a fourth. If I could have 2 volunteers, please, to help me with this for just a moment. If you'll take a hold of this one, and if you would be so good as to step over on this side, and you take a hold of this one. Now, what happens is that we can have these 2 molecules come together, and the sharing of the electron, let's see if we can maybe move this way just a little bit. The sharing of the electrons, this sp3 hybrid and this sp3 hybrid, ends up sharing electrons together, and that would form a bond. We would call that a sigma bond because it's located on a line between the 2 nuclei. And so we can begin to talk a little bit about sigma and pi bonding here. So this molecule would represent, if we had hydrogens out here on each end, this would be the molecule ethane that we have formed. And so that would have a nice tetrahedral type symmetry with that. Okay? So that would be sp3 hybridization, and that would show the formation of a single bond. Thank you. And I'll tell you what, if you just want to stand right there, we're going to come back and we're going to form the next process. In this case, we're going to go to the sp2. If we have an sp2, what we have are 3 orbitals that are identical. If you remember from the diagram that we had on the chalkboard a moment ago, we had 3 identical orbitals. So this is an sp2, an sp2, an sp2, and our carbazine in the center. The best I can represent would be this balloon to represent the bilobed p orbital. Remember that the p orbital has 2 lobes. So this is an sp2, an sp2, and an sp2, and here's a p orbital. The p orbitals form above and below the plane, and I'll give you that one to hold, and we'll construct one more of those. I am available for parties. 1-800-RENT-A-CLOWN. The kids always enjoy seeing all the balloons, and balloons are fun things to work with. And so, again, we have carbon with the same configuration. We have a single electron here, here, here. They are sp2 hybrids. The yellow balloon represents the p orbital that we did not hybridize. And now, if you would step in, what we're going to do is we're going to bring these 2 molecules together. So now we again have in the center the sp2 and the sp2 from the 2 carbons. They form a sigma bond between the 2 atoms. The unhybridized p orbital, hand up here please. Thank you. Hand down here please. Thank you. The p orbitals above and below the atoms overlap, and they form what is now called a pi bond. Pi bonds are difficult for students to visualize, and I don't even attempt to draw them on the board because they're much more complicated than my meager skills can do. But we get this picture now of what a double bond looks like. We've got the overlap of the p orbitals represented by the yellow balloons above and below, and the sigma bond that would be represented at the center. Thank you. We'll toss those to the side. And we'll form the sp hybrid at this point. The sp hybrid excuse me, has 2 orbitals which are hybridized. But remember from our diagram previously that it also has p orbitals that are unhybridized. Not 1, there's one of the p orbitals, but 2. So what we have represented here is an sp and an sp hybrid. The blue represents an unhybridized orbital here, and the yellow represents an unhybridized p orbital here. So we've got one of those. Thank you. We'll construct one more. Oh, anticipating. And for this, we're going to need a 3rd volunteer. So if I could have a 3rd volunteer up, please. So again, the same process that we had. We've got the unhybridized orbitals that are the p orbitals. I'll let you have that one. Let's see, we've got to orient it like this. And you're going to come around the back. Great. So in the center, as we've had before, this is an sp and an sp, and those overlap along the plane of the nuclei between the atoms. That forms a sigma bond. It's a sigma sp if you want to call it that. As we had before, hand on top, and down below, hand on bottom. You're great. That forms the p bond that we had before, the pi bond, and so there's the double bond arrangement that we had. Then, hand in front, great, and back behind. Yeah, this gets complicated. Now we have that third pi bond, which is located inside of that. So we have the sigma bond in the center, which is the stabilizing bond. We have one pi bond here, and we have the other pi bond around the center here. And that gives this nice visual picture for the students. If you want to get complicated with this, then you could actually have yet another set, and you could show a double bond, two double bonds next to each other, which also require sp hybridization to make that happen, depending upon what level that you want to move with your students. Thank you for the help there. You may be seated. The use of balloons to show bonding is not a new process, but perhaps the use of these long, skinny balloons would be a little bit of a different take and would help you to be able to explain to your students what a pi bond is, how a pi bond is different than a sigma bond, and what a multiple bond would look like inside of an atom. And so that's how we could perhaps use balloons to help us understand hybridization and multiple orbitals.